afternoon, everybody. The title of my presentation is the removal of copper and zinc from wastewater using Saudi activated bentonite. This presentation includes objective introduction, preparation of Saudi activated bentonite, metal removal experiment, adsorption isotherm, adsorption kinetic, and conclusion. The objective of this project is to evaluate the application of Saudi activated bentonite, which is a type of clay, for the removal of copper and zinc from wastewater. It is known that wastewater streams from metal industries such as electroplating, metal finishing, mining, battery manufacturing, piping manufacturing, use large quantities of water in their processes. These discharge streams from these processes contain toxic substances, heavy metals, acids, alkalines, and other substances. The problem is that the heavy metals in the wastewater stream can be absorbed by marine animals and directly enter the human food chains, thus presenting a health risk to the consumers. Copper and zinc are among the most common heavy metals in this wastewater, especially in some processes such as piping, manufacturing, and electroplating. The accumulation of copper in the human body causes brain, skin, pancreas, and heart diseases, while zinc, being in the list of priority pollutant proposed by Environmental Protection Agency, gives rise to a serious positioning cases. The maximum contaminant level of copper and zinc in the drinking water are 1.3 and 5 ppm respectively. So it's not recommended for these copper and zinc to exceed this limit in the drinking water. Copper and zinc as other heavy metals can be removed from wastewater using activated carbon. Actually, many methods can be used, which is like precipitation, flotation, ion exchange, but the most important one is the activated carbon, which is considered as the most used adsorbent. Nevertheless, it's relatively expensive comparing to clay materials. The alternative for the activated carbon is the activated clay. Clay minerals, as low cost and easily available adsorbent, have been extensively studied as absorbent for removal of heavy metals from aqueous solutions. In this project, we use the Saudi bentonite. The Saudi raw bentonite was collected from Khulais bentonite deposit, which is located 95 kilometers north of Jeddah. The Saudi bentonite is not active in its natural state, where some treatment was required in order to modify its adsorbent capacity. So the Saudi bentonite was received as ungrounded rocks. So crushing, grinding, and sieving processes were conducted before using the bentonite, Saudi bentonite, in order to reduce the size of the grains of the bentonite in order to do the treatment or the activation process. This is the experimental setup for the activation process. Actually, we tried different method of activation. We started with the calcination, then using hydrochloric acid, HCl leaching, then sulfuric acid leaching. The most efficient one is using the sulfuric acid. So this is the experimental setup. We can see the magnetic stirrer, the heater, and this is the reactor, and this is the condenser. So in the beginning of the experiment, we prepare as we told you before that about the bentonite, which was crushed and ground to about minus 100 mesh, which is about 75 micrometer. So in the beginning, we prepare sulfuric acid with a certain concentration and add it to the reactor and heat the sulfuric acid up to boiling. Then a certain amount of bentonite was added to the sulfuric acid, and the mixture was heated, kept boiling for a certain time with a continuous mixing. After a certain time, the mixture was removed from the reactor, filtered, washed to free it from acid. Then the samples were taken to the oven to dry it. We have many parameters we do trial and error to find out the optimum activation process parameters. So one of them, the sulfuric acid concentration, the temperature, the grain size of the bentonite, water to clay ratio, and we found that the acid activation was done using the optimum operating variables, such as the concentration of sulfuric acid was 15% by weight, the temperature of boiling, 90 minutes reaction time, grain size of minus 200 mesh, and water to clay ratio was 5:1. After doing the activation process, the samples, I mean the clay samples, dried sample, were taken to the adsorption process, which they call it the metal removal experiments. The adsorption of copper and zinc with activated bentonite was carried out using the batch reactor, or a batch technique, which is about by using the horizontal shaker with the water bath to control the temperature. In the beginning, a stock solution of copper and zinc were prepared by dissolving a appropriate amount of copper nitrate and copper and zinc sulfate in distilled water. Then the stick solution was diluted to obtain the standard solution containing 20 to 110 milligram per liter or part per billion of a required copper and zinc solutions. Then a certain amount of bentonite and 50 ml of metal, mils of metal solution at a desired initial concentration were added to 100 ml stubborn conical flask, and they were placed in the horizontal shaker. The flask were shaken in a horizontal shaker at 200 RPM. After a certain time, the samples were removed from the shaker, filtered, and the filter rate was measured to find the concentration of copper and zinc available in this filter rate using atomic absorption spectrophotometer. Then after that, actually we different factors affecting the removal process. So in this project, we investigate different parameters. These several factors, the absorption process, such as shaking time, solution, pH, metal concentration, clay dosage, metal removal efficiency, to find out the optimum factors or the optimum removal process. The result for this removal or absorption process, the effective shaking time on the removal of copper by Saudi activated bentonite was investigated using initial metal concentration varies between 20 and 100 part per million or milligram per liter. The clay dosage was 0.5 gram per 50 mils and the pH around 3.2. We can see from this figure that the absorption process or the removal process was fast, so that after about 2 minutes, about 44 or 43 percent of the copper was removed. So the process is fast, and we can see that the process's equilibrium was achieved after about 20 minutes. We can see for the different concentration that after 20 minutes the equilibrium was achieved. Another thing, we can see that increasing the concentration decrease the copper removal efficiency. So we can see increasing the copper concentration decrease the removal efficiency. The same process was conducted for zinc with the same condition. As we can see that after about 2 minutes, we found that about 50% of the zinc in the solution was removed, and the same increasing zinc concentration decrease the removal efficiency. So from this figure, we found that 20 minutes was enough or sufficient to reach equilibrium. So in the next experiment, we will use the 20% as the equilibrium for the process, or the time for each process after this process. We know that the pH is the most important factor in the absorption processes. So the effect of pH in the removal of copper and zinc was investigated using initial metal concentration, that means for the copper and zinc of 50 milligram per liter, with clay dosage of 0.5 per 50 mils, and the shaking time, as we said, is 20 minutes as the equilibrium time. We can see there is a gradually increase of the absorption or the metal removal percentage with increasing the solution pH until we get about 100% after at pH 7. Actually, decreasing the solution pH, that mean producing H ions in the solution, which compete with copper and zinc ions, and decrease the removal efficiency. When we increase the solution pH, that means we decrease the hydrogen ions in the solution, and then we increase the removal efficiency. But from literature, we found that in after pH 6, that copper precipitate as copper hydroxide. The same for zinc. They are the same. They precipitate after pH 7. So the process after pH 6 is considered as a precipitation and not absorption. Sorry, adsorption. Then we decided to use a pH before 6 for the next experiment. The effect of metal concentration were investigated using for the copper and zinc by Saudi bentonite using a clay dosage of 0.5 per 50 ml, and the pH, as I said, was controlled at 5.5, and the shaking time, as we took from the first figure, at 20 minutes. Effect of a clay dosage, we can see from this figure that there is a gradually decrease of zinc and copper in the solution, with increasing the initial metal concentration. This is because of the saturation of the adsorbent site. Actually, the activation process is what we did for the bentonite, the activation process is removing the impurities inside the pores of the bentonite. So these pores becomes active and attract the zinc and copper. So we see a decrease from this figure. We conclude that increasing the zinc initial concentration or copper the concentration decreases the metal removal efficiency or percentage. Effect of a clay dosage. We have to know what is the maximum or the optimum clay dosage we have to use with with the adsorption processes. The effect of a clay dosage on this and the removal of copper and zinc was investigated using initial concentration of 50 ml per gram pH 5.5 and shaking time of 20 minutes. We can see that this figure percentage, metal percentage, removal percentage versus clay dosage. Increasing the clay dosage increase the removal efficiency until we reach about 1.25 gram per 50 ml of per liter. That means after this, nothing will be added to the grains of the bentonite. So I think about 1.2 is the optimum for the concentration of 50 ml per 50 gram per liter of solution. The adsorption isotherm. Two adsorption isotherm models, the Langmuir and Friendlich equations, were used to fit the experimental data obtained from this work. Actually, we need isotherm to help in designing and modeling the process. The adsorption isotherm of copper and zinc removal were studied using different initial metal concentration at adsorbent mass of 0.5 gram and room temperature, and the solution was kept control at 5.5. We can see this is the Langmuir isotherm for the copper and zinc. We can see from this figure that the experimental data for the removal of copper and zinc were well fitted with Langmuir isotherm. We can see that the regression coefficient close to 1, and from that we can get the isotherm parameters. Q maximum, which is the maximum metal can be adsorbed per gram of the bentonite. For zinc it was 5.26 milligram per gram, and for copper less, as we found in the last figures. For copper 3.41, the constant P is 0.248 and 0.413 for copper. As well, the regression coefficient is close to 1, which is this model or the experimental data were well fitted with Langmuir isotherm. The same process for using other model, which is Friendlich isotherm. The process were well fitted. The experimental data for copper removal and zinc removal were well fitted with the Friendlich model. We can see the regression coefficient 0.9, which is close to 1, and for copper 0.99. The isotherm parameters at K equal 1.439, 0.6 for copper, N 3.1 to 0.6 for copper. It's known that from the literature that if N or a constant N between 1 and 10, that means the adsorption process is efficient. The adsorption kinetic, which is needed to study the reaction, the rate of the reaction. So the adsorption kinetic for copper and zinc removal were studied using 50 ml per gram of initial metal concentration, a clay dosage of 0.5 gram, and room temperature. The absorption data were analyzed using two kinetic models, the pseudo first order and the second order kinetic. The experimental data, as we see for the applying first order, we can see the data does not fit the first model because we have the regression coefficient of 0.18, which is far away from 1. The same for the copper. For the second order, we can see that the experimental data were well fitted with the second order reaction, where the reaction, the coefficient of the regression close to 1, so that the absorption we can utilize the constant we got from the absorption kinetic to design the process and to do the modeling for it. Conclusion of this project: the absorption of copper and zinc ions on Saudi activated bentonite was fast, and the equilibrium was reached after only 20 minutes. Removal of copper and zinc ions by Saudi activated bentonite is affected by solution pH. The absorption of copper and zinc decreases with increasing in the solution pH. Copper and zinc removal decreases with increasing metal concentration. When metal concentration increases from 20 to 100 milligram per liter, the removal of copper and zinc increases as the dose of Saudi activated bentonite increases. This is due to the increase in the number of adsorbent sites, as we said. The adsorption isotherm data were well fitted with both Langmuir and Friendlich models. Saudi activated bentonite can be considered as a promising adsorbent for the removal of copper and zinc from wastewater. By the end of this presentation, I would like to thank King Abdulaziz City for Science and Technology for their financial support to accomplish this project. By the end of this presentation, I would like to thank all of you for your attention, and if you have any question.
Any questions?
Any questions today?
Thank you. Thanks a lot.
It can be used in many of the cities.
Yeah, sure. That's right.
It's a low-cost process.
That's right.
Wastewater treatment.
Yeah, you are right.
Is